All right, I'm Jerry Pratt. I'm from the Institute for Human and Machine Cognition in Pensacola, Florida. I've got a great team of some really talented individuals there. Unfortunately, won't have time to name them all, but they all contributed. And these are the teams we had for the DARPA Robotics Challenge, which I'll talk a little bit about in my presentation. The hardware we use is the Valkyrie from NASA, which Josh talked about, and the Boston Dynamics DRC Atlas. We'd love to get the newest Atlas, but we can't, so we continue to operate this. But Boston Dynamics has been really great about keeping this robot supported, and NASA's really good at keeping Valkyrie up and running. Funding acknowledgement. Okay, let me start by just going over the video. This is sped up 15 times from DARPA Robotics Challenge because the robots were pretty darn slow, and it was 60 minutes of operation. So just to condense it down here. So we had to drive a car, get out. I'll point out a few things of what you're seeing here. The thing on the screen on the left is what the operator saw. So we had the camera view coming back from the robot, and then the 3D environment that was pretty much populated with LiDAR points colored by what the camera saw if the camera was intersecting with what the LiDAR was seeing. For the most part, the robot was kind of a mixture between pure teleoperation and, well, not quite pure teleoperation and some higher level things, but pretty much in the middle where the operator was saying, walk to this location and some footsteps would be determined. Put out affordance templates on things to move, so for example, the valve. And then we'd have some autonomous behaviors for turning the valve, but without much feedback. They're pretty much open loop scripts. Now we're starting to add a lot more feedback to make things a little bit more autonomous and faster. We had just a single operator, but there was 3 others of us kind of looking over his shoulder and having from practice a lot, kind of know what to look out for to give him feedback. But it was mostly John doing all the operation. There were some comm limitations, and that's really important for teleoperating robots. But they weren't very, very difficult limitations. There's a few seconds of delay in the high resolution imagery, but we got nearly continuous feedback, but low bandwidth, but you don't need very high bandwidth for joint angles of the robot. So the operator could have a really good sense of what was going on, even if you had delayed camera and LiDAR, because things weren't changing that quickly relative to what the delays were. And again, we didn't do any like pure teleoperation where you need really quick feedback. But like this task here where we're simply trying to put a connector back on it has a magnet in there. That took us a real long time because at this point there was about a 20-second delay in the video, and we're doing visual feedback, the human was. So we'd move it a little bit, wait about 20 seconds to get a clip, move it a little bit, so we could have, that's something that could have been really sped up. And then for footstep planning, we just individually put out individual footsteps. I'll talk a bit more about some autonomous footstep planning we've been doing since then. So some of the lessons learned, I think, are that these sort of systems are definitely feasible for real world tasks, but one, they need to be a lot faster. One thing we did in the DARPA Robotics Challenge was made sure anywhere we put autonomy, and we continue to do this, it's called coactive design approach of autonomy, is make sure everything's observable, predictable, and directable. So a lot of times, people try to make things fully autonomous where you push the button and the robot completes the mission. And then when it fails, you're frustrated. And you're like, why is the robot doing that? What's he going to do next? How do I know what he's doing? So we try to build in, even when we have, especially when we have autonomy, build in a lot of feedback to the operator. Even if you give them, the operator, like really low level information, like raw LiDAR points, it really helps for the operator to have good situation awareness. Communication delays can and will be a major factor, especially in things like space exploration. And there's still a lot of work to be done. Particularly, I think, is the robots need to be able to survive falls and get back up. That was kind of one of the major limitations of the DARPA Robotics Challenge, was whenever any of the humanoids fell down, and we fell down a couple times, you took a penalty and the robot got set back up, and it was kind of embarrassing. So that's one of the things we really want to fix now, is design robots that can survive falls. Okay, as far as avatar robots go, people have been talking about these things for quite some time. This is a really old picture of some different robots that were out on the market. I think about 10 years ago. There's probably another dozen companies trying to sell these things now. I hope they do really well. We have a double bot, which is second from the right, second one on the right. And I love it, but we don't really use it too often, and you don't really see them very, very often. The fact that there's none here is kind of surprising, seeing that this is what we advocate for. But we need to make them better and maybe get the price down. I'm not, who knows what the commercial pushes are and pulls, but it'd be nice to see more of them. As far as what we want to get to is similar to the movie Avatar or Surrogates. But in both of those cases, they had really good brain-machine interfaces. We don't have those, but we do have some really nice VR headsets and other interface devices that you've seen from the previous talks, and they keep getting better and better and better. Same with the sensors. They keep getting better and better. On the left is what we had in the DARPA Robotics Challenge, which was a LiDAR and camera, which back then cost somewhere in the multiple tens of thousands of dollars. These things keep dropping in price to the point where some things available now are just a few $100s that are just about as good or much better. So this shows John here teleoperating Valkyrie using a system where instead of it being pure one-to-one mapping, he's kind of telling the robot what to do through the input. And then, unfortunately, you don't get to see it here, but he can then preview what the robot's going to do before he tells it to actually do it. So after, let's see here, you often see John doing a bunch of clicks that the robot's not moving. He's actually interacting with the interface, getting some commands queued up. So that's one way of doing these, where if you don't, especially if you have a time delay, as Josh was showing, you might want to queue up some commands, get some feedback as to what you expect to happen, and then execute them. This is one thing we did. I don't think this is how you would actually control walking, but here we're individually placing footsteps in the world as just a couple footsteps in front of the robot as he's walking, so that there's no delay waiting for the next footsteps to come. The operator's in the virtual world and just goes down and actually physically places a footstep on where he wants it to step. So we gave John the challenge here to get over the terrain, get the ball off the trash can and throw it in the trash can, in the smaller trash can. So now he's doing the manipulating again, where it's not direct one-to-one. You see his motions aren't exactly mapped, but once he likes what he sees, then he clicks a button and the robot will move. And then here's some autonomous footsteps. Since it's flat ground, no need to place them himself. And then walks over and throws it in. So that was about a minute to do this. We're still talking about a factor of 5 slower than a human, but I think we can start making that a bit quicker. Here's one of the world's humanoid avatar pioneers. So we had Marco Rubio in the lab a couple years ago, and he did the task that you just saw John do, get over the terrain, the part of it. And he was able to do it with about 5 minutes of training. So there's a lot of potential here. Let's see here, so these, I guess, aren't synchronized videos. I apologize for that. But here's Servan Bertrand. This is some direct teleoperation he's doing now, where it's doing whole body control. So if he goes down to the ground, the robot will squat down to reach. And also making sure the robot doesn't do any self-collisions and maintains balance. So if you go way over where the robot can't balance, it'll prevent itself from falling. And if you try to have the robot hit itself, it'll prevent itself from hitting itself. And all that's built into a big optimization problem that solves for all those things. So you have input coming from the VR interface. We're doing whole body IK adding balance, collision avoidance, and also joint position and velocity limits. For the collision avoidance, we just use really simple primitive shapes right now, just because general polytopes are slower, but you could do any shapes you want. Here you'll kind of see the delay between what's coming from the virtual reality interface device and what's coming out of the algorithm. They're a little bit delayed because of the velocity limits. And I don't know if you'll see it here where I'll do, no, I guess not. If you do something like try to push your arm into your waist, the robot will shift its weight over so that it doesn't hit itself. So the Oculus Quest is one of the newer things on the market, really incredible. I just wanted to show this because I thought it was really neat. I got this demo the other day. This is 3 people in the same interface. On the right here, you can see somebody just using a webcam or a phone camera to show what the virtual world sees. So all those crazy people running around, what they're actually seeing. And so the robots are in the same virtual environment, and the response is so quick that you can run around without bumping into each other. And you can do things like, give each other high five and things like that. It's pretty cool. I don't know if that'll be how we actually control robots, but these devices are incredible. And the Quest is only about $400 and everything on board. And it's pretty nice. Okay, so why humanoids? I think it's pretty obvious to everybody that you want hands. You want to get into your virtual environment if you're going to do any real work, hands. But why legs? It's a good question. And we want to be able to get to the same places that humans can get to. If you look at the difference between bipeds, quadrupeds, wheeled vehicles, and tracked vehicles through a lot of different environments, humans have amazing dimensions for getting through things. So we're really small where it matters. Foot's only about 3 inches wide. And we're really large where it matters. We can grab something 7 feet high with no problem. Whereas something like a wheeled vehicle would need an enormous wheel to get over things. So you'd have these enormous robots in order to get over the same things that a 5 or 6 foot tall human can. For climbing ladders, you need kind of legs. And yes, dogs can climb ladders. It's pretty incredible. And of course, you're quadrupedal when you're climbing a ladder. Humans are quadrupeds. We just only go quadrupedal when we need to. Now, when it comes to narrow things, that's where we really shine, because we're just so tall and narrow. If you wanted something like a wheeled vehicle to be able to get through a narrow passage, the wheelbase would have to be smaller than the passage itself, so it'd be a tiny little robot. Yeah, and dogs can walk on balance beams. Stepping stones, of course, you need intermittent contacts, so you simply can't get over them with wheeled tracks, and we can reach high places. So if you put all these things together, 2-legged things are really good at just about everything human does, since humans are 2-legged, and the others are good in a lot of places, but not great in all of them. So if you think about operations in a typical disaster of an environment, this is my garage, and there's places where you got to squeeze in between, climb over things, etc. So it kind of really highlights the need for legs. But legs require active balance, and that's what makes humanoids much harder. I won't get into strategies for that. We do use a whole body motion control framework that I also won't get into too much. I'll just keep showing some fun videos. Here's what the robot can do. So here's Atlas walking over a variety of large rocks. This is sped up about 4 times. And this is the operator interface, and this one is just the operator giving individual footsteps. But there are times when the robot will fall off a step and be able to balance and just keep on going. So I think we're, as a field, we're getting to the point where we kind of understand balance and understand walking. And getting to the point where we can almost do human level equivalent walking. As far as balancing on one foot, I think we can get to the point where we're superhuman pretty easily because our sensors are better, the robot sensors are better than human sensors. Your feedback loops are much quicker. So this is standing on the side of a 2x4, which is quite challenging. Or I mean, it's a side of a piece of plywood. Here we have cinder blocks tilted on their side, so you have line contact. And what the robot's doing is putting its foot out and kind of moving its center of pressure around to detect what kind of contact it has. And then knowing that it doesn't have a good contact, realizing that, okay, when I take the next step, because it takes me a long time to swing my leg, I'm gonna have to use my upper body a little bit to balance. So use its upper body momentum, move its arms around a little bit like you would if walking on, say, a railroad track. Here's another view of it. See there, it took quite a bit of a lunge. Okay, so moving on to footstep planning. What we've been doing recently is a two-stage planner where we generate a body path just looking at planar regions in the world. So we've taken our LiDAR data and from the LiDAR points figure out where there's good flat surfaces. So to find the ground, top of tables, whatever, cinder blocks. And then using those, using a really pretty straightforward visibility graph approach, figure out a good path through them without considering the footsteps yet. Then once we have the body path, then consider where to put the footsteps afterwards. And the reason we do that two stages is because if you're considering where to put the footsteps and you get into a situation where you like have the cul-de-sac problem where you're stuck somewhere, it might take, you might be looking at millions and millions of possible footstep locations when really you got to get out of that cul-de-sac before you can make progress. And so you don't really need to know where the individual footsteps are going to go. You just need to know, yes, there probably is a path this way to get to the goal. And then once you know that, look for the individual footsteps. And then we've done some, set up some fun situations where the robot can do some path planning. To avoid self-collisions of the leg swing, we just use a pretty simple heuristic that if you detect that you're going to collide, just have the leg swing out a little bit using like a 4-point spline on the leg trajectory. This is showing planning up and down rough terrain. This is sped up about 4 or 8 times. Every April during Robotics Week open house, we'll have about 1,200 people come cycle through. So this year, this is one of the demos we gave, and we just had the robot going up and down its terrain for about 3 hours. But it's fun to operate. This kind of shows how if the path is blocked, the robot will, in real time, just look for a different path. Again, using the body path planner before the footstep planner. All right, so what do I mean by co-exploration of hazardous environments? Well, a lot of people today talked about different potential applications. I think the best applications for telepresence avatar robots is where you want human presence, but it's too dangerous or expensive or remote to get there. If a person's on the other side of the world and you don't want to fly there, there's that expense. If somebody's on, if you want to explore Mars or the moon or maintain the habitats, that's really expensive. The bomb technician is very dangerous. Perhaps firefighting, especially in situations where it's too dangerous to send a firefighter in because the building's already structurally unsound, but maybe you could send in a robot. A lot of different potential applications. It'll be interesting to see if any of these come to fruition, both technically and from just a point of view of the markets. You can never predict what people are going to want or to pay for. And I think for a lot of these that we're getting to the point where the systems we have can achieve acceptable performance. A human will, for a long, long time, a human's going to be better in every one of these situations. But if we can cross a certain threshold of acceptable, level, then maybe there will be some economic viability. I'll show a couple cooperative things here. This is showing one way you could control a robot to help carry something. All this is doing is looking at the interaction forces. Previous talk had shown a similar algorithm, looking at the interaction forces on the robot, and from that determining the intention of the direction you want the robot to walk. So a couple lines of software there to do a pretty neat task. One day we decided to just see if we could simulate putting out a fire. The fire department was gracious enough to hook us up. They wouldn't let us start a fire. They said it just would have been a mess anyway and not added much to the demo. But the Office of Naval Research had been interested in robots for firefighting on ships. And so here we kind of just showed that you could have some pitching motion of a simulated ship in water, and without any changes to the walking algorithm, the robot was able to continue walking. After we did the DARPA Robotics Challenge, we just thought, hey, it'd be neat to see what else we could do using the same interface. So John one day just spent a day trying a bunch of things like moving pallets from with a pallet jack. He was able to do a lot of things, but you see that the speed up is 20 times because these were things he had never done before. We had no autonomy for it. It was pretty much just, here's an interface for doing one set of tasks. Let's see if it's general enough to be able to do some other things, and show that physically these robots could potentially do these things if we can get some better interfaces and some better software to do them more quickly. And I think a big application for robots is entertainment. Hopefully we'll get to the point of something like Real Steel someday. And having really compelling fighting robots that are as amazing to watch as humans boxing with some human operators would be really cool. All right, so towards humanoid avatar robots, we got a long way to go. If you look at what humans can do, it's just phenomenal. This is one of our goals for our upcoming robot, is to be able to get over pile blocks like this. Or, in a lot of disaster zones, you have stairwells that have rubble. So even though a lot of wheeled and tracked robots can go upstairs, no problem, it's hard to get over the rubble piles that are on the stairs. There's been a lot of enabling trends, especially in anything that doesn't make contact with the world. So non-contact sensors, all the LiDAR, cameras, computers just keep getting faster and faster, communication's great. And then all the algorithms for perception, vision, the virtual reality interfaces keep getting better and better and cheaper. Localization and mapping is nearly a solved problem now. Obstacle avoidance, and then a lot of the things coming on with deep learning and data-based algorithms. There's really, in this category of things, there's really no end in sight as to how amazing things can get, and relatively quickly, and become really, really inexpensive. The major challenges are where the rubber hits the road. So actuators and transmissions really haven't been getting terribly better over the last 3 decades I've been working on this stuff. A lot of the mechanical components. I think we can do a lot in joint designs, come up with better joint designs, but to a point. Power sources are still limited, batteries. Skin sensing's making some good progress. It'll be great once we see that be used a lot more. I think it's getting to the point where you'll see it a lot more. And hand designs are getting really good. Getting hands that can both do fine manipulation and large forces and be able to survive falls. That's going to be tough. But maybe what we'll do there is have like a hand changer, so that when you're getting through your complex environment, maybe you just have a simple gripper for opening doors that's really robust. And then when you get to where you actually have to manipulate something, you do your tool change and have a really high, high precision, but maybe not so robust hand. So here's, on that front, here's some of my wish lists. guess I won't go over to them, running out of time here. But if you think about just the challenge of trying to emulate a human, it's super hard, especially some of the degrees of freedom that are really high range of motion. So if you look at your shoulder and your hips in particular, where you have your ball and socket joint, well, if you look at your shoulder, you've got your 3 degree of freedom ball socket joint, but you also have 2 degrees of freedom of shrug. So up and down, forward, backwards. So you got a 5 degree of freedom mechanism right there with about, less than a liter of volume being used for all its actuation, or maybe a little bit more than that. And muscles are amazing for many reasons, but I think one reason they're really amazing is that they allow for joints like balls and sockets where you're not completely captured, you're just kind of resting against it. Because we have ball and socket joints as mechanical engineers, but they can only move about 60 degrees because they have to hold that whole ball in there. Well, with a biological ball and socket, you get 180 degrees of motion and 3 degrees of freedom, because the muscle is what's holding it together. You can dislocate your shoulder, but the muscle and the tendons keep it all held together. If you wanted to make a similar system with the actuators we have with, say, linear pistons, you would need, for those 5 degrees of freedom, there's a dozen or 2 dozen muscles pulling on that. You would need all these actuators that can't touch each other, so they'd be breaking each other as they're hitting each other, so you need more and more and more volume, and it just gets really complicated. That's why we typically use bearings and single degrees of freedom instead of trying to emulate a shoulder. But if we can start moving towards these types of degrees of freedom. So a couple years ago, Victor Ragusolo, who's here, he got his PhD from Toronto, and he was looking to do some consulting work, and I talked to him, and I'm like, hey, why don't you start thinking about what it would take to make a humanoid gymnast? He's like, okay, I will. I'm like, no, this is impossible. You cannot do it. Like, okay, I'll give it a try. So what we wanted to do is see if we could match, how closely we could match the degrees of freedom, the joint range of motion, the power, the weight, and the volume of a human. So Victor is originally from Romania. So of course he needed to call the robot Nadia. And then we've been joined, Sebastian Sanchez is here too. So if you guys have any questions about this robot, talk to these two guys. This is a mock-up of our robot. So this is 3D printed plastic. This is version 3 or 4. One thing we're trying to do is go through a number of versions before cutting in any metal, because as all of you know who have worked with robots, as soon as you cut metal, your mistakes are in metal and expensive and hard to undo. 3D printers are so amazing now and so cheap that we can go through a lot of design revisions before we actually commit to something. So and it's also a nice way to see what the range of motion of the robot is, see if we can get it to crawl and transport nicely in a ball, that sort of thing, and pose it in some use cases. So we've been using the Moog integrated smart actuators. We're pretty much designing the robot around this. This is the same actuator used in the Italian Institute of Technology's, their newest HiQ robot. It's 3D printed titanium piston that has the servo valve, the pressure sensor, the position sensor, release overflow valves, and all the plumbing all in one package. So normally, if you did this in individual components, it'd be about 2.5 kilograms. These guys are about 1.6 kilograms and are pretty compact. The reason we choose hydraulics is power to weight ratio. The solid red line here is torque speed curve of a human. The blue dotted line is if you put a good effort into making an electric actuator at about 2 kilograms. And then the red dotted line is what you can get out of a hydraulic actuator at about 2 kilograms. The Moog ones are actually a little bit lower because the servo valve they choose is just a little bit lower flow rates, but it still almost covers the solid red line. So no, I don't think we can build humanoid gymnasts, but we can start moving towards that goal. Humans are just too amazing. They're super flexible. They're super strong and fast. These are torque speed curves we've used from human walking and human running, and some of the actuators we're looking at to try to match those curves. Really challenging to do. But I think we can, especially with hydraulics, you can match the torque speed curves, but matching the range of motion is near impossible. As I said, we try to do rapid design iterations, but we're getting to the point now where we're almost ready to build the first prototype for real. We're using in the knee a crossbar mechanism. In the hip, we're using a dual 4-bar linkage. That gives us good range of motion. We get about 80% the range of motion of a normal human in the hip. In the knee, we can get the full range of motion, and the ankles get near full range of motion. We've been making, so we really want, as I said before about the DARPA Robotics Challenge, you really need your robot to be able to survive fall and get back up. So we're going to try to make the whole body carbon fiber exoshells that can survive a fall. If you think about humans are pretty fragile, but if you put on some hockey equipment or football equipment, you can fall on from pretty high height and not get hurt too badly. So if the robot's kind of built in the same way, we might be able to survive some falls. This is a test stand testing the knee and the hydraulic actuator. And doing some really deep knee bends. Yep, so the robot's coming along. Like I said, if you want to learn more about it, talk to Victor or Sebastian. And thanks for your attention.